Okay, so um, today's 13th. Okay, we're going over homework number 7, number 9. So homework number 7 says cars arrive at a gas station with a Poisson distribution with the mean of 10 per hour. Determine the probability that over the next hour, only one car will arrive. Okay. I think so. So let X be a Poisson distribution that tells you the number of arriving um, at a Shell station. And the mean, so the expected value, the expected value of this distribution is 10. And so part A asks, determine the probability that over the next hour, only one car will arrive. So they're asking for what's the probability that X equals 1. So you have to remember the Poisson distribution, which is e to the negative lambda times lambda to the I. Well, this is if this were to be I, right? Over I factorial. And we know that lambda is the expected value of the Poisson distribution. So what we have here is the probability that X equals 1. This is e to the negative 10 times 10 to the first power over 1 factorial. And if you put that in your calculator, you get what? You get e to the negative 10 times 10. And you get 0.000453999297.6. And of course, this goes on forever. So this is the probability. And if you want to, write it as a scientific notation, 5.39 times 10 to the 1, 2, 3, 4, negative 4 power. So that's also another way you can express the probability. Okay. Yeah, e to the negative 10 to the negative 4. And so when you plug it in the calculator, you want to make sure that you put as many decimal places values, as many values after the decimal place as possible. Because if you don't put everything, right, if you only put like the first 4 or 5, it may not be considered as correct. Okay, and then part B. Yeah, part B says compute the probability that in the next 4 hours, more than 27 cars will arrive. So then I want more than 27 cars will arrive. So what do we do here? I want the probability that X is what? more than 27, right? So greater than 27, but then you want the complement, right? Um, more than 27. So then you want 1 minus the probability that x is less than or equal to 27. I mean, pardon me, 26. But I think you can also use your calculator for this. You can use the Poisson CDF because that would make more sense to use than the PDF itself because you have an accumulation of. So let me share my screen with the calculator. So if we go to second distribution here, second vars, which is distribution, you have the Poisson CDF and lambda is 10. And of course here the x value is up until a particular x value. So if you do up until 26, you're gonna find a probability of 0 when x equals 0, 1, 2, all the way to 26. So when you get that, you get 0.99999. And I think that um, that's a little too much. Um, a bit different. Hold on, let me see. This is the one with uh, in the next 4 hours, more than, yeah, in the next 4 hours. Um, more than 27 cars will arrive. And the thing is, the random variable is for every hour, right? So this random variable is not 4 hours, but for every hour. This is per hour. Wait, so Hijab, what were you saying with the complement exactly? I thought you'd subtract the probability. Yeah, so x is the random variable is the random variable that we're dealing with, the probability distribution is per hour. So 10 per hour. Compute the probability in the next 4 hours, more than 27 cars will arrive. So per hour, there's about 10 that arrive. Um, so that's an interesting problem here. Because it appears that we should do the cumulative distribution, but then you get a number that's really, really high, 0.999. That's the only concern I have at the moment. In the next 4 hours, let's see, it says, so we have the next 4 hours, but B doesn't really matter, it appears. The number of hours doesn't really affect the answer. 7. Wait, what if I do 27 instead? Yeah, so I'm gonna get back to this one. Okay, this one's a little. Have you multiplied the lambda by 4? If I multiply it by 4, oh, I see what you're saying. Oh, okay. That's, I see. I see what you guys are saying. Yes. So essentially, okay, got it. So essentially, thank you guys for this one. There's a in the sense you're making a new random variable. In the sense you're saying y is the number of cars arriving at a Shell station in 4 hours. But y is really 4x. And that's why the expected value of y is 4 times the expected value of x, which is 40. So this is 40 cars. This is the expected value or the average number of cars in 4 hours. And then what you want is that you want the probability that y is greater than 27, which is equal to 1 minus the probability that y is less than or equal to 27. Because in the world of discrete random variables, y greater than 27, right? The complement of this is y less than or equal to 27, because this is saying more than 27. This is at most 27. So that's right. So then when you compute that now using your calculator, you go back to second vars, use the Poisson CDF, and your expected value is no longer 10 because we're not dealing with per hour, we're dealing with every 4 hours, so it's 40 instead, and the x value is 27. And so the idea is that we're computing all the probabilities when x equals 0 all the way until x equals 27, which indicates the number of arrivals at the station. Could be 0, could be 1, all the way to 27. But of course, after we find that number, we do 1 minus that, because that's the complement. So you do 1 minus the answer, and you get 0.98066 dot 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 dot. And that would be your answer. So yes. Thank you for that. The y equals 4x thing. You can, so this is where you can take a random variable and then you can make it another random variable, a function of it. So so that's pretty helpful to have. Okay, good. So, okay, good. So any questions about this further from here? So the next one Next one is homework number 10, number 5, right? Okay, homework number 10, number 5. Yeah, these are kind of sometimes uh they're hard, not necessarily because of the concept itself, but about the bounds, right? That's the hardest part of these problems, is the bounds. So homework number 10, number 5. So we have a joint probability density function of x and y. And oh, pardon me, yes. Pardon me for that. Okay. So we have 0 otherwise. And then we got x is between y over 14, negative y over 14, and 0, y is between 0 to infinity. So before even doing anything, I immediately pay attention to this. Immediately. So when I pay attention to that, I want to see what that looks like. I want to see what that region is like. So I first want to graph the region. Graph the region that f of xy is defined upon. Again, we're dealing with something in the, this is really a function. If you were to graph it, it's in the three-dimensional space. X and y, you consider it as the domain, right? This is the domain of the function. And then the value of the function is the z value. So usually when you learn differential integral calculus or multivariable calculus, you're dealing with functions z as a function of two variables, x and y. Okay. So I want to see what the region looks like that that f of x is defined upon. And the bounds are given by, or the region is given by this restriction. Y is between 0 and infinity. So that's an easy one. And what we know is that x is between y over 14 and bigger than negative y over 14. So what I look at is this is really the key. This is the key. This is the key inequality. So if you study this, y, like just look at this inequality here. We get x is less than or equal to y over 14, or in other words, y is greater than 14x. And what is that necessarily? That's a line, right, that goes through the origin. And it has a pretty steep slope, right? Y equals 14x. But it says y is bigger. Y is bigger. So if y is bigger, then I'm shading above, right? But the thing is, it's also y, yeah. And then if you look at this other inequality here, it says negative 14y is less than or equal to x. So if you solve for y and you multiply by negative, you switch the sign. Y is also bigger than negative 14x. Okay, negative 14x is the same thing, but it's going in the opposite way. So we got this. We got y equals negative 14x. So do you see that? So what we're saying is that this region that we're shading is all of this. So does everybody see the region? So x is bounded by these two lines. Okay. So that's very helpful now, because now when we have to do our integration, double integration business here, it's a little bit easier to see what the bounds will be. So it says find C. So the first part of it is find the value C. Find the constant value of C. So we know that if you're a joint PDF of any sort, if you integrate over the region, right, over the entire thing. So actually, if you integrate negative infinity to infinity, negative infinity to infinity of f of xy dx dy, you must equal 1, right? That's just the axiom, a probability axiom. Okay, so once we have that, now we have to look at the bounds. So we know for a fact that y goes from 0 to infinity. And then x, they're telling us x is between. So we don't have to really do too much here, actually. Negative y over 14. They're telling us x is between that. And then we got c multiplied by y squared minus x squared. Y squared minus 196 x squared e to the negative y dx dy must equal 1. So we do the inside integral first, because we're in differentiate or integrating with respect to x. All the y, this y here, because it's multiplied to everything else, and this c can be placed out in front of the first integral. Well, c can be placed out in front of the both the first and the second integral. So I'll do that. So c is out here. This goes from 0 to infinity. Then I got e to the negative y integral from negative y 14 y over 14 y squared minus 196 x squared dx, and then dy is equal to 1. Then you can integrate this with respect to x, and you get x y squared minus 196 x cubed over 3. And you're evaluating this from y over 14 to negative y over 14. E to the negative y from 0 to infinity of c, right? This equals 1. Okay, so far so good. Now we have to plug in, right? So, and there's a dy here. So when we plug in, I'm gonna do this step by step, okay? So I don't want to make mistakes, which is very easy to do here. So I'm gonna call this 1 here, and this is 1. So xy squared minus 196 x cubed over 3, y over 14, negative y over 14. And you plug that in, you get y cubed over 14 minus 196 over 3. I'm going to put that like that. And I got y over 14 cubed minus, parentheses. When I plug that into x, I get negative y cubed over 14 plus, this becomes plus 196 over 3 multiplied by y over 14 cubed. Okay. Now, 196 is really 14 squared. So with that in mind, I can rewrite a couple things here just to help out with the calculation. So this is 14 squared over 3 and multiplied by y cubed over 14 cubed. And then you distribute that negative, this becomes a positive y cubed over 14 minus 196 over 3 multiplied by y cubed over 14 cubed. Sorry, this should be 14 squared. Now the 14 squares cancel, so I'm left with only 114 in the bottom. And so I'm left with y cubed over 14 plus y cubed over 14, which is 2y cubed over 14. And I get a y cubed over 3 times 14 minus y cubed over 3 times 14. That's minus 2y cubed over 3 times 14. Okay. And then I can multiply it here by 3 over 3 to have the same denominator. So this becomes 6y cubed over 3 times 14 minus 2y cubed over 3 times 14. And I get 4y cubed over 3 times 14. And I can simplify this to be a 2. This would be a 7. And then my final expression here would be 2y cubed over 21. So this just became like a Calc 2 problem, right? With all this integration. But any questions about this first integral that we did? No, we're all good. Okay, so this becomes c multiplied by the integral from 0 to infinity of e to the negative y times 2y cubed over 21 dy equals 1. So we can put the 2 over 21 outside of the integral. So this becomes 2c over 21 from 0 to infinity of y cubed e to negative y dy equals 1. And now, is there an easy way to do this integral? This is really saying the expected value of y cubed. There's no easy, clear cut way. Yeah, I thought there might be a cleaner way, but integration by parts it is. So then you make a u equal y cubed. U prime is 3y squared. V prime is e to the negative y, and v is negative e to negative y. This is going to happen or occur quite a number of times iteratively. So then we get negative y cubed e to negative y evaluated from 0 to infinity. And this becomes minus, but then it becomes a plus afterwards from 0 to infinity of 3y squared e to negative y dy. Now, if you study this here, when you plug in infinity or when you make y approach infinity, this expression goes to 0 much quickly than this goes to infinity. So that whole expression goes to 0. And when you plug in 0, you also go to 0. So this whole expression here just goes away, disappears. This becomes 0. And then you have this integral here where you do the same thing. You say u is equal to y squared in this case, U prime is 2y, V prime is e to negative y, V is negative e negative y. And so you have this 3 in front, and you do the same thing again. You get negative y squared e to the negative y from 0 to infinity. This becomes plus 2y to negative e to negative y, dy from 0 to infinity. By the same reasoning, why this goes to 0, this expression here goes to 0, this goes to 0 as well, by the same idea. And then I get this. I got 3 multiplied by, and this becomes 2. And then you do it one more time. You do the integration by parts one more time. You make u equal to y, so u prime is 1. V prime is e to negative y, so v is equal to negative e negative y. And then you get y, negative e to negative y from 0 to infinity, plus the integral from 0 to infinity of e to negative y dy. But this here, actually, I think we could have just finished it here. Yeah, because when you integrate this, we know that this will equal 0. And this here, when you integrate this, you get e to negative e to negative y from 0 to infinity. When you plug in, when this goes to, when y goes to infinity, this expression goes to 0. This becomes minus e to the 0th power, which is minus a negative 1, which is positive 1. This will equal 1. So when you multiply this, you get 3 times 2, which is 6. So this entire integral is 6. So you get 2c over 21 times 6 equals 1. You can cancel out the 3. This becomes 2. This becomes 7. So you get 4c over 7 equals 1. So c is 7/4. So as you can see, a lot of integration in this section here, and this topic of joint probability distributions. Not so much the probability, the concept of probability is present here. It's more just applying the rules of integration. So is that part okay? Are we good with finding C? Okay, now to complete this problem, we need to find, the last thing we needed to find was what? The expected value of X. But to find the expected value of X, what do we need to know beforehand or first? How would we find the expected value of X only when we have a joint distribution of X and Y? Well, it's not the marginal of Y, it's the marginal of X, right? We want to find what is the marginal density function of X. Right? So this is what we want. We want f of X. But that entails taking the joint distribution function, joint density function, and integrating all of Y. But Y goes from 0 to infinity. So it's this thing here. We already know C is 7/4, so 7/4 from 0 to infinity of, and what was it? This is y squared minus 196 x squared e to the negative y dy. So we want a function only of x, right? That's the idea. Now for this, it looks like we may have to do two integrals because you have to distribute that y. We get 0 to infinity of y squared e to the negative y dy minus 196 integral from 0 to infinity of x squared e to the negative y dy. But this x squared I can place out in front actually. So let me do that. And we already did this integral here. It's equal to 1. So we know that's going to be 1. And we already did this integral here as well. Or we can actually compute this because this is the expected value of y squared, right? And we know that the expected value of well, we know that, what do we know? We know that the, didn't we do this one here, y squared? We did it right here, didn't we? And when we computed this, what was the result? Out of all of this, what was the only value that came out? What was it, 2? Right? This was equal to 2. So we get 7/4. This is a 2 minus 196 x squared. So we can write this as 7/2 minus, I think 196 is divisible by 4. 196 divided by 4 is 49 times 7. 343. So when you multiply the 7/4 and distribute it, you get 343 x squared. So this is the marginal density function. And then we want the expected value. We want the expected value of x. So remember what the expected value of x is x multiplied by the marginal density function from negative infinity to infinity. And the bounds here are symmetric. If you study this, this is an even function. If you multiply an even function, so this is even, right? An even function is a function that's symmetric along the y-axis. So it's symmetric if you reflect it across the y-axis. And if you multiply that by an odd function, which is x, the result is an odd function. And there's a little tidbit on odd functions and even functions. So if note, this is from Cal 2, if f of x is odd, then the integral on a symmetric bounds of integration for your function is immediately 0. Why? Because odd functions, right? If you know what odd functions look like, they're symmetric across the origin. They have point symmetry. So the area that's accumulated on one end, right, is the same area accumulated on the other side of the integration bound. But the thing is, it's going to be negative. It's going to be the opposite area. So that's why these areas here will always cancel out on a symmetric bound for odd functions. That's one. The second one is if f is even. If f of x is even, then when you integrate an even function on a symmetric bound, you could really do what? You can double the integral from 0 to one of the side, the upper half of the bound of f of x dx. So this is just only useful for simplifying integration. So if I were to integrate this on a symmetric bound, x multiplied by 7 halves minus 343 x squared dx, I should already understand that this will be 0 because this is an odd function. And we have a symmetric bound. So the expected value of x is 0. Oh yeah, no problem. This is very useful for integration. So it just helps with integrating odd and even functions on a symmetric when you have symmetric bounds. Okay, great. Great. Okay, anything else? What else? What else should we go over on from the homework? Again, you have until Wednesday to try to get as high as possible on the homework assignment. It's gonna be open until Wednesday night. So problem number 3 for homework number 10, is that what you're asking, right? Yeah, that one is probably one of the harder ones on this homework assignment. This one is a little bit lengthier as well because of the integration that's required here. So again, we have this joint probability density function c x squared minus y squared e to the negative 2x. And this is when x is between 0 to infinity. And when y is between negative x and x, this is 0 otherwise. Okay. Again, let's study the region where the probability density function is defined. So to do that, again, we draw the xy plane. This is x, this is y. In this case, now, if you see x is between 0 to infinity, and y is between x and negative x. So if you study this inequality, y is less than x, what you're going to be drawing now is y equals x. But I want this y to be less than that, so I'm going to be shading downward. At the same time, y is bigger than negative x. What's negative x? This diagonal line. But y is above it. So this is my region. Very important to understand what region I'm in. So this is where f of x is being defined on. Everywhere else is 0. Doesn't have anything. But in this triangular region that goes on forever, you have this function that you can actually graph. All right. Isn't that positive x? Which one is positive x? This is y equals positive x. No, this is not positive x. This is negative x. Y equals negative x. The slope. So think about, I know when we do like more advanced mathematics, the basic mathematics sometimes gets lost. It just happens. But y equals negative x, right, is a linear function whose y-intercept is 0 and whose slope is -1. So if you were to graph y equals negative x, you get this line, right? Because it has a slope that's negative. But the reason why we only want this piece is because x is positive. X is positive, right? This x is positive. But we're saying y is negative x. So if x is positive, then y is negative. The x. Do you see that? So the bottom is y equals negative x. Does that make sense? Yeah, this is just fundamental aspects of linear functions. So we want my y, so it's really about the y, not about the x. It's about the y. My y values, I want it to be between negative x and x. So when x is positive, y is below that positive x value. And at the same time, that y value, whatever that is bigger than negative x. Okay, so once we have that established, what we want is, so this is the tricky part, right? We want the conditional probability of x given y. So we want the conditional probability of x given y. And y is a y value bigger than 0. The notation is the notation in your homework assignment is actually a little off. It should be f x given y, and this should be x given y, not x comma y. It should be x given y. Okay. Now, conditional probability works the same way as if we were doing the probability that A given B is equal to the probability of A and B over the probability of B. We're just applying this now to conditional probability. So this should be the joint probability of A and B is it's like saying the probability of A and B. The joint probability of X and Y is like saying the probability of A and B. So this is the joint probability above. That's the numerator. And in the denominator, we have the probability or the density here of Y, the marginal of Y. Do you guys see that? It follows from this kind of probability, conditional probability definition. Correct? So the real question is, what is the marginal density function? That's really what the question is hinging upon. So I want to know, what's the marginal density function of y? So remember, to find the marginal density function of y, you have to integrate the joint probability with respect to x. Okay, and we go from -infinity to infinity, right? But now let's study this a bit more. It says that x is from 0 to infinity, right? But the thing is, it's saying that we want a given y value. We're given a y value. So go back to your region and select the y value that's bigger than 0, because we want a y value bigger than 0. So choose any y value bigger than 0, right? This y value here is bigger than 0. Okay, I got it. Now, once we have that defined, once we have that y value defined, we want to integrate all of x. And what that means is we're really going to be highlighting this this horizontal line. So once y is established, what are all the x values? The x values go from the y value, because here y equals x, right? Y equals x right here. So the x values range from y to what? Infinity. That is why the bounds here is y to infinity. Does everybody understand this? This is the hardest part of this. Everything else is just integration and the technical aspect of integrating. You're just writing positive y because that captures y. Yeah, y is positive, but the point is it's a given y. They're giving you a y value that has to be positive, right? Not just any y value, but one that's positive. So everything that's up here. Choose one. I'm given one. I don't care what it is. It's just one of them. Now, based upon that, right, I want to integrate over all the x values to get just what the y value would, just to get the marginal density of y. That's what we normally do. We just integrate over all to find y, the marginal density of y, integrate all over what x could be. But given a y value, x can only be y to infinity. It can't be anything below it, right? Given this y value here. If I was over here, my x values for this particular y value only ranges from all this whole horizontal line. So the moment you select the y value, the only x values that are associated with that y value are all the ones along the horizontal line. Because if you do anything on the other side of it, right, these x values here are not in the region. They're not within the region. So if you understand that aspect, then that's why you would understand why the integral is as so. It's saying what are the x values range from given the y value being bigger than 0. Well, the x values range from all the all the x values being y to infinity, and that's because of the nature of this region, geometrically speaking. Okay. So once we have that, then we can integrate, right? C times the integral from y to infinity. Again, this is the hardest problem in the set, and probably one of the harder homework problems because of those little minor technical details. So this becomes x squared minus y squared, and all the integration that we have to do here in e to negative 2x dx. Now you may say, hey, but we need to know what c is. Actually, you don't. Why is that? Because f of x of y is c times x squared minus y squared e to negative 2x, right? And then you're dividing this by c multiplied by the integral from y to infinity of x squared minus y squared e to negative 2x dx. As you can tell, the c's here cancel. The constants cancel. So you don't really care about the c values because they cancel out very nicely. So this c will just hang in there for now. And we're really just concerned with the integral here. So this becomes the integral of y to infinity of x squared minus y squared e to negative 2x dx. If you separate the integral into two integrals, you get y to infinity of x squared e to the negative 2x dx. And then you get minus the integral from y to infinity of y squared e to the negative 2x dx. Okay. So we're going to do this step by step as well. So this is number 2 and this is number 3. So what's number 2? And the integral from y to infinity of x squared e to the negative 2x dx. So there is no slick way other than just to do it. So u equals x squared u prime equals 2x, v prime equals e to the negative 2x, v is negative 1/2 e to negative 2x. Plug it in and you get negative x squared e to the negative 2x over 2 evaluated from y to infinity plus the integral from y to infinity of x e to the negative 2x dx. Now, when you plug in infinity, make this go to infinity, this again will go to 0 quicker than this goes to infinity. So the entire thing goes to 0 when you plug in infinity or when you approach infinity. And you do minus, or you do minus this negative when you plug in y, and you get, what do you get? You get positive y squared e to the negative 2y over 2. And then you do plus, and then you get x e to negative 2y. So again, you do the same thing. You do u equals x, u prime equals 1, v prime equals e to negative 2x, v is negative 1/2 e to negative 2x. So then you get negative x over 2 e to negative 2x evaluated from y to infinity plus 1/2 y to infinity e to negative 2x dx. When you plug in infinity for this guy here, again, you get 0, and you plug in y, you get y squared e to the negative 2y over 2 plus y over 2 e to the negative 2y. Just see everything's okay. It looks okay so far. And then the integral of this guy is e to the negative 2x negative 1/2 from y to infinity. Again, you get the same thing. This goes to 0, and then you get positive 1/2 e to the negative 2y. Okay, so that's what you get for this integral. Now let's look at the next integral here. 3. So this is going to be my integral here. Then you get the integral from y to infinity of y squared e to negative 2x what is it? Dx. Now, because it's with respect to x, you can take out the y squared, you get y squared, and this becomes y to infinity of e to negative 2x dx. And I think we just did this one, right? Wait, hold on. We did this here, right? This is e. So if you plug in infinity, this is half. This should be 1/4. It should be 1/4 because you're multiplying the 1/2 to this 1/2 when you plug in the y. So it should be a fourth. But we did this one here. Yeah, we did this one here. So if you did this one here, this would be positive 1/2. So this is y squared times positive 1/2 e to negative 2y. So you get y squared over 2 e to negative 2y. Okay? Now let's put that all together. Let's put that all together, and then what do we get? So if you take 2, which is this here, and you subtract it with 3, which is this here, you get that the integral from, what was it? This integral here this is equal to y squared over 2 e to negative 2y plus y over 2 e to the negative 2y plus 1/4 e to negative 2y. This whole thing is 2. And then you subtract that from 3, which is y squared over 2 e to negative 2y. But then you cancel this term with this term, and you're left with y over 2 e to negative 2y plus 1/4 e to negative 2y. That's that integral. I know, it's long. It is long because it's only part A. So this integral, we can make this a little smaller. I mean, we can make this more compact by factoring out the e to negative 2y. And you're left with y over 2 plus 1/4 e to negative 2y. And if you wanted to, you can, let's see if we can make this the same denominator. So this becomes 2y plus 1 over 4 e to negative 2y. So you can write it as 1/4 2y plus 1 e to negative 2y. And all of this is in the denominator of our marginal density function, of our conditional density function here, of our marginal y, right? We're putting this in the denominator over this. So our final answer, fx given y, x given y, is equal to this is x squared minus y squared e to negative 2x, and you're dividing this by a fourth 2y plus 1 e to negative 2y. Let me just make sure. Just make sure this is all okay. It's very easy to make a little tiny mistake given all the integration that we've done. Got the 1 plus 2y, the 8, 4. Yeah. Yep, I think this is, of course, it's not clean. To make it more clean, um, this 1/4, I can put in the numerator by making this a 4. This is x squared minus y squared. Now we have the same base here, so we subtract, right? So this becomes e to negative 2x plus 2y. If you factor out the negative, this becomes e to negative 2x minus y. So this becomes e to negative 2 parentheses x minus y. And all of this is divided by 2y plus 1. And this craziness is part A. For this problem, you have to calculate the joint probability density function. Well, they give you that. You don't have to. You don't have to compute the joint. They give you the joint. What you have to compute is the marginal, and that's what gave us the most problem. The marginal density function of y, which was all of this, right? Which is not too crazy, but it's still a lot to keep track of. So then once you're able to combine that and find the marginal density function, which is here, this is it, right? This is the marginal density function of y, which I found. Now I put that expression here in the bottom of the joint density function to find the conditional of x given y. Again, this is the joint divided by the marginal density of y. That gives you the conditional. And then all I did was the algebra. And e to negative 4x, hijab, I'm not exactly sure how you got negative 4x, because these are two different variables. X and y are different, right? You have x and y, so you can't combine x and y. Oh yeah, it could be. It could be the input for the question. Yeah, it could be that yours joint distribution is a different number. The numbers will change, but the structure of the problem is the same. It's gonna be something similar. So you have to do all of this. Yeah. Sorry. It's a bit of work, you know. It's a bit of that's a lot of bookkeeping, really. But I remember I took the what was it? At one point in time, I was considering doing actuarial science. So then I took the if you guys know about being an actuary, you have to take 10 exams over the span of like 10 hours. I mean 10 hours. Over the span of 10 years or so. And the first exam is a probability exam. So it's all of this plus more. And it's 3 hours and it's 30 multiple choice questions. So it sounds doable, right? But when you're actually doing it, every problem is like this one. The amount of integration that you had to do to complete one problem was a lot of steps of integration steps. So it was very easy to make one little calculation error. You had to be on your P's and Q's with this. But imagine having 20 of these, I mean 30 of these similar kind of problems with integration involved within a span of 3 hours. So that you're pressed for time. The moment you got the exam, you were pressed for time already. That was an interesting experience. I'll be holding office hours only for today. Wednesday is no class. There is nothing. Wednesday, I believe, you may or may not have um, you may or may not have finals. Okay, so then after this step, the rest of that problem, right, is the same idea. For y given x is the same idea. You find the marginal density of X, and then you divide that by, but the difference is for part B, you have to do one more extra step. For part B, you have to integrate your density function. So for part B, right? You want to find the you want to find this, and this entails integrating this, the density, which is dy. Yeah, it's to find the integral of, well, yeah, this is of x. It's a different variable, dt. But to find this, you have to find the joint distribution and divide it by the marginal distribution of x, which is the same thing as saying f of x comma y over the integral of f of x comma y dy. So you have to first do this step divided by this function, and then integrate that to get the cumulative distribution. So it's a bit more steps for part B. All right, guys. Why you have to integrate this one? Because they're asking for what? The cumulative, they're asking for the distribution, the distribution function, not the density function. And remember, whenever you see the uppercase f, you're dealing with cumulative distribution. The lowercase f, you're dealing with density. The uppercase f is the integral of the lowercase f. The lowercase uppercase matter in this regard. It matters. The uppercase f, well, is always attributed to the cumulative distribution function. The lowercase f is always attributed to the density function. And the cumulative is the area underneath the density function. Henceforth, the integral. All right, guys, so this is officially the last Zoom meeting. Officially. Congrats. Pat yourselves on the back. I don't know. Pop some champagne. Not sure what you guys do when you celebrate, but hope you guys can celebrate. And before you guys go, you want, oh, sleep is a great idea. Yeah. Have time. Shouldn't take that long, right? CUNY that. Yeah, I think this is the link to the course evaluation. So please take some time, 5 minutes. I don't know how long it take you, but it shouldn't take too long to fill out the course evaluation. It would help me very much to see. Oh, they closed today. Oh, they closed today. Yeah, so even more so. And most likely, what they always do this, but they always like tell you a certain date that they're gonna close, and then they say, "Oh, it's been extended." This and there. So I have a really high. The possibility is very high that they'll just extend it. But anyways, regardless, take some time today to just evaluate the class honestly, and of course, if you have any criticism, do so constructively. And I believe it's anonymous, so I won't be able to see anybody's name. So you can be as forthright as possible, and it will help me so to gauge exactly how you guys felt with a raw perspective, which is good. So it can help me improve anything for next time, which I will have next semester, 241 again. So, anyways, Thanks, guys. I'll be in office hours later. For those of you who need more help with the homework, I hope you guys take advantage of completing all the homework assignments and maximizing your homework grade. And we have a final next Monday. I may have more review sessions later this week. Okay, I'll let you guys know about that. And I will post one more review sheet. It's going to be a lot shorter though compared to the other ones. It's going to be everything covering after exam 2. So all this joint distribution stuff will definitely be on it. And that's it. That's all I can say. That's all I got. Will there be even number of questions from every topic or more questions for the topic after the midterm? Will there be even number of questions from every topic? Oh, I see. I see what you're asking. I see what you're asking. Is there going to be an equal distribution of questions from every topic, or will there be more emphasis on the things after the first exam, second exam? Um, that's a good question. It's hard to say at the moment. It's hard to say, but what I can say is that definitely there will be questions on the stuff that hasn't been tested from exam 1 and exam 2. So all this joint distribution um, aspects definitely will be on it. As if it's more of an emphasis, then that's hard to gauge at the moment. Um, but just be prepared for questions from every topic, any topic. It's not, I can't do all topics. I can't do that because then it'll be a 4 hour, it'll be a 6 hour exam. I'm not trying to do that. I'm trying to keep it a 2 hour exam. So yeah. All right, guys. So yeah, so please fill out the course evaluations and I'll see you guys. All right. Take care, everybody. You made it. You made it to the end. Bye bye.